Right now, in every direction you can look, the galaxies thin out. And for 1 billion light years, in every direction from where you are sitting, there are roughly 30% fewer galaxies than there should be. It is not that they are missing. The space is not empty. It contains stars, gas, dust, dark matter, galaxies of various sizes. It contains the Milky Way, in which you are situated, and the Andromeda Galaxy, 2.5 million light years away, and the entire local group, and the larger structure called the Laniakea supercluster. But around all of that, extending 1 billion light years in every direction, there are fewer galaxies than the standard cosmological model predicts. The density is, by careful count, about 70% of the cosmic average. The region is, technically, what cosmologists call an underdensity. We sit inside it. Tonight we are going to walk through what that means. You do not need to hold every number. Some you will. That is enough. The hole we are about to discuss is not the kind of hole that swallows things. It is a region of space, not a hole in space. The hole is, in some sense, gentle, a quiet pocket of the cosmos where galaxies are slightly fewer than the average region of the universe. But the quiet pocket has implications that, when we sit with them, redraw the picture of where we are. We have a couple of hours. If you have come here to rest, let this carry you. The void we are about to walk through is not threatening. It is, in some sense, the quiet pocket of the cosmos where we happen to live. Now let us pull back. Let us look at what the discovery of this pocket actually consisted of, and how we came to know that we are inside it. The story begins in 2013. In that year, 3 researchers at the University of Hawaii published a paper in the Astrophysical Journal titled Evidence for a 300 megaparsec scale, underdensity in the local galaxy distribution. The 3 researchers were Keenan, Amy Barger, and Lennox Cowie. Their work, combining decades of accumulated galaxy survey data, identified a region centered approximately on our galaxy that contained significantly fewer galaxies than the broader cosmos. The region became known after their initials as the KBC Void, the K for Keenan, the B for Barger, the C for Cowie. The paper was not the first hint that something was unusual about our local volume. Earlier surveys, going back to the 1980s, had detected hints of underdensity at smaller scales. The Butter's Void, identified in 1981, had shown that vast, underdense regions could exist in the cosmic web. The Great Wall and other large-scale structures had mapped the distribution of galaxies at scales of hundreds of millions of light years. The general picture, by the time Keenan and his colleagues began their analysis, was that the universe is structured in a vast web of filaments, walls and voids, with galaxies clustered along the filaments, and the voids representing the empty spaces between. What was new about the 2013 paper was the scale. The underdensity Keenan and colleagues identified was approximately 300 megaparsecs in radius. 300 megaparsecs is approximately 1 billion light years. That is a scale at which the universe is supposed to be uniform. The cosmological principle, which has guided our thinking about the universe since the early 20th century, says that the universe should appear roughly the same in all directions and at all locations, on sufficiently large scales. The principle is built into the standard models of cosmology. It allows us to use equations developed in our local neighbourhood and apply them to the universe as a whole. It assumes that we are not in any special location. A void of 1 billion light years radius is, by the standard model, not supposed to exist. The model predicts that at scales of 100 to a few hundred megaparsecs, the universe should average out to its mean density. Any larger underdensities should be rare. The probability of a 1 billion light-year underdensity containing the Milky Way is, by standard calculations, less than 1 in 100,000. The KBC Void, as identified in 2013, is 6 standard deviations larger than what the standard model expects. This is not an outlier you brush off. This is, if it is real, a feature of the cosmos that we have not yet fully accounted for. The paper was, when it appeared, a quiet announcement. The Astrophysical Journal does not typically print sensational claims. The paper was technical. The conclusions were carefully worded. The implications, however, were profound. If the KBC Void is real, our local cosmology may not be representative of the cosmic average. This was, in 2013, an interesting result. Over the subsequent decade, the result has been refined, debated, and brought into contact with other puzzles in cosmology. Most notably, it has been connected to what is now called the Hubble tension. I want to walk through the Hubble tension carefully, because it is what makes the KBC Void story potentially urgent. Now let us pull back. Fellow Night Watcher. The Hubble constant is one of the most fundamental numbers in cosmology. It describes how fast the universe is expanding. Specifically, it tells us how much faster a galaxy at twice the distance is moving away from us, compared to one at a given distance. The relationship is linear, at least at moderate scales. Galaxies twice as far recede twice as fast. The slope of that linear relationship is the Hubble constant. The units are kilometers per second per megaparsec. The first reliable measurement of the Hubble constant was made by Edwin Hubble himself in 1929 at Mount Wilson Observatory in California. His original estimate was about 500 kilometers per second per megaparsec. The number was too high by about a factor of 7. It was wrong because of systematic errors in distance determination. But the linear relationship he identified was real, and his name is attached to it. Over the subsequent 90 years, the measurement of the Hubble constant has been refined many times. The methods have included direct measurement using the distance ladder, in which astronomers use Cepheid variable stars to calibrate distances to nearby galaxies, and then use brighter standard candles like type Ia supernovae to extend the reach to greater distances. The methods have also included indirect inference from the cosmic microwave background, the leftover radiation from the early universe, combined with the standard model of cosmology. By the early 2000s, the two methods had converged to roughly the same value. The Hubble constant was approximately 70 kilometers per second per megaparsec, with uncertainties of a few percent on each side. The agreement was, by the standards of cosmology, comfortable. The methods were independent. The agreement suggested that the standard model was working. Then, around 2013, the agreement began to dissolve. As the distance ladder methods improved, the local measurement of the Hubble constant settled at approximately 73 kilometers per second per megaparsec. The cosmic microwave background measurement, with the high-precision data from the Planck satellite, settled at approximately 67 kilometers per second per megaparsec. The difference on its face is small, 6 kilometers per second per megaparsec out of 70, about 8%. But the precision of each measurement has improved to the point where the difference is statistically significant. The error bars on each measurement are tight enough that the two values are now incompatible. The probability that the two measurements are consistent given current uncertainties has dropped to less than 1 in 100,000. This is what is now called the Hubble tension. The tension is, in some sense, the central puzzle of modern cosmology. The standard model, which has been remarkably successful at explaining nearly everything else about the universe, predicts a single Hubble constant. The local measurements give one value, the cosmic measurements give another. The two cannot both be right in the simple form of the standard model. Something is wrong. What it is, we do not yet know. There are broadly two classes of explanation for the Hubble tension. The first class says that there is new physics. Some aspect of the standard model is wrong or incomplete. Possible candidates include new particles in the early universe that affect the cosmic microwave background, modifications to the behavior of dark energy, exotic interactions between dark matter and other particles, or extensions to general relativity itself. Each of these candidates is being actively investigated. None has been confirmed. The second class says that there is no new physics. The discrepancy arises from something in our measurement methodology. Perhaps the distance ladder has unrecognized systematics. Perhaps the cosmic microwave background interpretation has hidden assumptions that are wrong. Perhaps our local volume is somehow not representative of the cosmic average. The KBC Void hypothesis sits in the second class. It says that we live in an underdense region. In an underdense region, the local expansion rate appears faster than the cosmic average, because the underdensity allows the contents to spread out more quickly. The local Hubble measurement taken in our underdense bubble gives a higher value than the true cosmic average. The cosmic microwave background measurement, integrating over the entire history of the universe, gives the true average. The difference is real, but it is not new physics. It is the difference between local and global measurements in a universe that is not perfectly homogeneous. This is an attractive explanation for the Hubble tension. It does not require new physics. It only requires that the universe be slightly less homogeneous than the standard model assumes. The hypothesis has its critics. Some calculations suggest that the local underdensity, even if real, would not be large enough to explain the full Hubble tension. The underdensity needed to fully explain the tension would have to be larger than the KBC void identified by Keenan and colleagues. Other calculations, based on different assumptions about how the void interacts with the cosmic expansion, suggest that the KBC void is just barely large enough to do the job. The debate is active. The matter is not settled. Let me hold this for a moment. The Hubble tension is, at present, one of the most important unresolved puzzles in cosmology. The puzzle could be resolved by new physics. The puzzle could be resolved by understanding local cosmography. We do not yet know which. If the KBC void hypothesis is correct, then our home is a region of the universe that is not, in some sense, typical. Our cosmological measurements made from inside this region are biased. Our understanding of the cosmic expansion may need to be adjusted for our particular location. If the KBC void hypothesis is wrong, then the Hubble tension demands new physics. The implications of that for our understanding of fundamental cosmology would be even larger. Either way, the story matters. Let me hold the Hubble tension a little longer because the texture of the disagreement is worth understanding. The two methods used to measure the Hubble constant are, in some sense, very different. They probe very different epochs of cosmic history. The cosmic microwave background measurement looks at the universe at an age of approximately 380,000 years. At that time, the universe had cooled to about 3,000 Kelvin, electrons and protons had combined to form neutral hydrogen, and the radiation that had previously been scattered off free electrons was free to propagate. The radiation, redshifted by the subsequent expansion of the universe, now reaches us as a faint glow at microwave wavelengths. The pattern of fluctuations in the cosmic microwave background contains information about the conditions of the early universe. The acoustic peaks in the angular power spectrum tell us about the geometry and contents of the universe at that early time. Combined with the standard cosmological model, this data lets us infer the Hubble constant. The Planck satellite, which collected cosmic microwave background data from 2009 to 2013, produced the most precise such measurement to date. The result, after careful analysis, was a Hubble constant of about 67.4 kilometers per second per megaparsec, with an uncertainty of about 0.5%. The distance ladder measurement, by contrast, looks at the universe in its current state. It uses nearby galaxies to extend a chain of distance determinations outward, eventually allowing us to relate distance to redshift. The slope of the relationship is the Hubble constant. The state-of-the-art distance ladder measurement, performed by Riess and collaborators, has been refined over many years. The most recent results give a Hubble constant of about 73 kilometers per second per megaparsec, with an uncertainty of about 2%. The two results disagree by approximately 8%. The uncertainties on each are small enough that the disagreement is statistically significant. The probability that the two measurements are consistent, given their stated uncertainties, has decreased over time as the precision of both measurements has improved. This is the situation. Two different methods, both well calibrated, both checked across multiple independent approaches, give different answers for the same quantity. Something must be wrong. The KBC void hypothesis is one of the candidate explanations. The hypothesis says that the local distance ladder measurement is biased upward by our location in an underdense region. If we correct for the local environment, the local Hubble constant should drop to approximately the cosmic microwave background value. The tension would then resolve. Whether this works in detail depends on the size and density of the void, the specific distances at which the supernovae are observed, and the structure of the corrections that need to be applied. Various analyses have come down on different sides. Some find that the KBC void is sufficient to explain the tension. Others find that the void is too small or too shallow to do the job. The matter is at present unresolved. Now let me bring this closer. I want to describe in a careful way what the KBC void actually looks like, because the picture is not, in any visual sense, of a hole. It is not of a region you could see from outside as a darker area on a cosmic map. The void is a statistical feature. It is identified by counting galaxies in different volumes of space and comparing the counts to the cosmic average. Inside the void, the count per unit volume is approximately 70% of the average. Outside the void, the count is roughly average or higher. The void is, in this sense, a region where galaxies are slightly less common than they should be. The reduction is uniform in roughly equal amounts in every direction. The Milky Way sits roughly at the centre of the underdense region, though not exactly. There is some offset. The boundary of the void is not sharp. The density does not drop abruptly. The density gradually decreases as you move from the cosmic average region into the void, reaches a minimum near the centre, and then gradually increases as you exit the other side. The transition occurs over hundreds of millions of light years. If you were to take a galaxy survey of the universe and colour-code it by local density, the KBC void would appear as a soft, irregular blue region, denoting underdensity, embedded in a broader background of yellow and red, denoting average and overdense regions. The blue region would have an irregular shape, with hints of the cosmic web structure that surrounds it. It is not a sphere. It is not symmetric. It is a roughly defined underdense region, observed in galaxy counts with the Milky Way somewhere near the middle. Stay with me here. Let me also walk through what the void looks like in the broader context of the cosmic web. The cosmic web is, by current understanding, the large-scale distribution of matter in the universe. It consists of dense filaments where most galaxies live, connected by walls and surrounded by voids. The web has been mapped by many surveys, but our knowledge is still partial. The Sloan Digital Sky Survey, conducted over the past 2 decades, has mapped roughly a quarter of the sky out to redshifts of about half. The MNRAS survey covered the entire sky in infrared, identifying galaxies that would be missed by optical surveys due to dust extinction. The 60F Galaxy Redshift survey covered the southern sky. The DESI survey, currently ongoing, is producing the highest resolution map yet. From these surveys, we can build 3-dimensional maps of the local universe. The maps show the cosmic web clearly. Filaments stretch between groups and clusters, and voids occupy the spaces between filaments. The web extends in all directions, fading into the distance as the surveys reach their depth limits. When we look at our particular location in these maps, we find that we are in a relatively underdense region. The filaments around us are present, but the spaces between them are slightly emptier than in other parts of the map. The clusters in our neighbourhood are real, but slightly less numerous than the cosmic average would predict. This is the KBC void as it appears in the maps. The maps are, in some sense, the most direct visualization of the void we have. They show the underdensity. They show our position within it. They show the gradual fading of the underdensity as you move outward through hundreds of millions of light years. What is missing from the maps is the matter that does not emit light. Dark matter, by current understanding, makes up roughly 85% of the matter in the universe. The cosmic web is, in some sense, primarily a dark matter structure. The galaxies we see are the visible markers of the underlying dark matter scaffolding. If we could see the dark matter directly, the void would still be there. The underdensity we observe in galaxies is, by current understanding, mirroring an underdensity in the underlying dark matter. The dark matter is, in some sense, the foundation. The galaxies are the buildings on the foundation. Both are sparser in our local region than in the cosmic average. This is the part that is hardest to hold. The void does not look like anything. It is not photographed. It is not directly observed. It is inferred from statistical analysis of galaxy survey data. The inference is robust in the sense that multiple independent surveys agree. The MNRAS survey, the SDSS survey, the 60F Galaxy Redshift survey, the DESI survey, all show below-average galaxy counts in our local volume out to roughly 1 billion light-years, but it is statistical in the sense that the underdensity is small, 30% below the average. This is not a 100-fold reduction. It is a moderate effect, identified through careful counting. The effect would not be detectable, even today, without the cumulative work of many surveys and careful comparison to theoretical predictions. The detection is, in some sense, a triumph of patient observational cosmology. Now let me hold the implications for how we are situated. If the KBC void is real, then our position in the cosmos is, by current understanding, somewhat unusual. We are not in a typical region. We are in a region that, in the standard model, should not exist with the probability we observe. We are, in some sense, in an unlikely place. The unlikelihood is not enormous. The standard model says that voids of this size should occur, but rarely. We happen to be in one of the rare cases. Or, alternatively, the standard model is wrong, and voids of this size are not as rare as predicted. Either way, our location is informative. It tells us something about the universe. KBC. If we are in a rare void, then our existence in this void may have been, in some sense, a contingent fact. Most observers, in most parts of the universe, would not be in such a void. We happen to be. If voids of this size are common, then the standard model needs revision. The universe is less homogeneous than we have assumed. Other observers elsewhere might also be in voids of comparable size. We do not yet know which is correct. Let me also hold the question of why our location might be in such a void. The answer, by current understanding, is that voids form naturally in the evolution of the cosmic web. In the early universe, just after the Big Bang, the distribution of matter was nearly uniform but contained small fluctuations. The fluctuations are visible today as anisotropies in the cosmic microwave background. They are small. The amplitude is about 1 part in 100,000, but they are not zero. As the universe expanded and cooled, the fluctuations grew under the influence of gravity. Regions that started out slightly overdense became more overdense, as they attracted additional matter from their surroundings. Regions that started out slightly underdense became more underdense, as their matter was drained away by the surrounding higher density regions. Over billions of years, this process produced the cosmic web we observe today. The filaments are the regions that started out slightly overdense. The voids are the regions that started out slightly underdense. Our particular location, in this picture, was a region that started out somewhat underdense in the early universe. Over the subsequent 13 billion years, the underdensity grew, eventually producing the KBC Void. This is the natural explanation. The void formed from primordial underdensity. The underdensity grew. We happened to form within it. The fact that we formed within it, rather than in some other region, is, in some sense, a contingency. Different observers in different parts of the universe would form in different local environments. We happen to be here. Others elsewhere would experience their own local environments. The probability that any given observer would find themselves in a void of the KBC void size is, by standard models, small. This is the puzzle. We are in a relatively rare type of location. The question is whether the rarity is consistent with the standard model, or whether the rarity points to something the model is missing. The debate continues. Now let us pull back and let us walk through how the void was actually identified. The methodology is, in outline, simple. You count galaxies in concentric spherical shells centered on the observer, and you compare the counts to what the standard cosmological model predicts. If you are in an average region, the counts in your shells should match the model. As you go to larger shells, you sweep up more galaxies. The ratio of count to volume should be approximately constant, except for known small-scale fluctuations. If you are in an underdense region, the counts in your inner shells will be lower than the model predicts. As you go to larger shells, eventually you will leave the void, and your counts will return to the average. The transition happens at the void boundary. By looking at galaxy counts as a function of distance, you can map out the density profile of any local underdensity in any direction. The Keenan, Barger, Cowie analysis did exactly this. They used K-band galaxy counts from the 2-mass survey, combined with redshift information from various follow-up programs, to count galaxies in shells out to several hundred megaparsecs. The counts came in below the model prediction. The deficit extended to roughly 300 megaparsecs. Beyond that, the counts returned to roughly the model prediction. The interpretation: we live inside a region of approximately 300 megaparsecs radius that is underdense by roughly 30%. Subsequent analyses by various groups have refined the picture. Whitbourn and Shanks in 2014 found a smaller but still significant underdensity. Hoscheit and Barger in 2018 mapped the void in 3 dimensions and confirmed its shape. The DESI survey, currently producing data, will refine the picture further over the next few years. The cumulative picture is that the void is real, though its exact size and shape are still being refined. The underdensity is between 20 and 30%. The radius is between 500 million and 1.5 billion light-years, depending on how the void is defined and which dataset is used. These are not small uncertainties. They reflect the difficulty of measuring large-scale structures from inside them. But the existence of the void, in some form, is robust. The deficit is detected by multiple independent surveys. The pattern is reproducible. What we have is the void. Let me also walk through the dynamics of voids in expanding universes, because the dynamics are themselves an interesting story. In an expanding universe, a void is not a static structure. It changes over time. Specifically, as the universe expands, the matter inside a void spreads out faster than the matter in an average region. The void becomes emptier relative to its surroundings. The boundaries of the void move outward into the surrounding higher density regions. This is, in some sense, what voids do. They expand. They become more pronounced over time. The rate of expansion of a void is set by the standard cosmological dynamics. For a void of the KBC Void size and depth, the void boundary moves outward at roughly a few % of the speed of light, in a frame that is comoving with the cosmic expansion. Over the age of the universe, the boundary has moved a substantial distance. The boundary motion has several consequences. The underdensity at the centre of the void becomes more pronounced over time. The walls surrounding the void become thicker as material drains into them from the interior. The galaxies inside the void recede from each other slightly faster than they would in an average region. This is the local expansion rate effect that contributes to the elevated local Hubble constant. It is, in some sense, the dynamical signature of the void. Over cosmic time, the void grows. Over the next 10 billion years, the underdensity will become more pronounced. The void will spread outward. The walls will continue to thicken. This is the long-term future of our local cosmic environment. We are in a void. The void is growing. Slowly, over very long timescales, our region of the cosmos is becoming, in relative terms, emptier. Now let me bring that closer. What does it mean to live inside a cosmic underdensity? The first thing it means practically is what I have already mentioned. The local expansion rate, measured by the recession of nearby galaxies, is elevated compared to the cosmic mean. The Hubble constant locally comes out higher than it would in an average region. The second thing it means, less practically but more philosophically, is that we are not in a typical region. The cosmological principle, which assumes that we are, is wrong in detail for our particular location. The universe is, on the scale of 1 billion light-years, not perfectly uniform. We are in an underdense pocket. The third thing it means is that our cosmological measurements, made from inside this pocket, may need correction. We have, in some sense, been doing cosmology in a slightly anomalous laboratory. If we want to extract the parameters of the universe as a whole, we need to account for our local environment. These three implications are connected. They all flow from the same observation. The local density is not the cosmic mean. The question is what to do about it. Stay with me here. The standard cosmological model, the lambda CDM model, has been remarkably successful at explaining the universe at large scales. It accounts for the cosmic microwave background, for the abundance of light elements, for the growth of structure, for the accelerating expansion. It gives a coherent picture of how the universe has evolved from its hot, dense beginning to its present cool, expanded state. The model is built on the assumption of homogeneity and isotropy at large scales. The KBC void, if real, weakly violates that assumption in our local volume. The violation is not dramatic. The underdensity is 30%. The void is 1 billion light-years in radius. On scales much larger than that, the universe averages out to the cosmic mean. The cosmological principle holds on the larger scales. It just does not hold perfectly at our local scale. The lambda CDM model can, with appropriate modifications, accommodate a local underdensity. The modifications are not trivial. They involve corrections to how we interpret local measurements. They involve potentially revising our value of the Hubble constant after accounting for the local environment. The work is ongoing. The model is being refined. The local cosmology is being mapped in more detail. What we have at present is a tentative picture. The picture says that we live inside a 1 billion light-year underdensity. The picture is supported by multiple lines of evidence. The picture has not been definitively confirmed. The picture has implications for the Hubble tension, which may or may not be the right resolution. The picture is, in cosmological terms, very recent. It has been developing over the last decade or so. The full implications are still being worked out. Let me also walk through the relation of the KBC void to other voids in the cosmic web. The cosmic web is, in some sense, a network of voids, with the filaments and walls being the boundaries between them. Some voids in the cosmic web are well known. The Boötes void, identified in 1981, is one of the largest known voids, about 250 million light-years across. The Eridanus supervoid, identified in 2007, is another large structure. There are dozens of named voids, identified by surveys over the past several decades. Most of these named voids are at distances of hundreds of millions to billions of light-years from us. They are external voids, in the sense that we are not inside them. The KBC void is different in that we are inside it. The void contains us. Our local cosmology is set within it. The distinction between internal and external voids matters because the cosmological effects are different. For an external void, the underdensity affects how light propagates through it on its way to us. For an internal void, the underdensity affects our entire local environment, including our local expansion rate. The KBC void is the largest known internal void. It is the void we live inside. It is the void whose properties affect our cosmological measurements. Other observers, elsewhere in the universe, might be inside their own internal voids. They might have their own cosmological biases. The biases would be different from ours. Their measurements of the cosmic Hubble constant made from their local environment might give different values than what we measure. In principle, by comparing measurements from many different observers, we could average out the local biases and recover the true cosmic value. In practice, we cannot do this directly because we cannot communicate with observers elsewhere. We have to infer the cosmic value from our single location, with appropriate corrections. The corrections are what the KBC void hypothesis is about. The hypothesis says that we need to correct our local measurement for our local environment. The correction, if done correctly, should bring the local Hubble constant in line with the cosmic value. Whether this works in detail is, again, an open question. The work continues. Now let me pull back and let me try to give you a sense of the scale of all of this. 1 billion light-years is a large distance, larger than the Milky Way by a factor of approximately 10,000, larger than the local group by a factor of roughly 100, larger than the Virgo supercluster by a factor of roughly 10, larger than the Laniakea supercluster, which contains the local group and many neighbouring structures, by a factor of approximately 3. The void encompasses many superclusters. It contains thousands of galaxy clusters. It contains tens of millions of galaxies. It is not, by any meaningful sense, a small structure. It is a significant feature of the cosmic web. The cosmic web as a whole has been mapped by many surveys. The web consists of filaments, walls, and voids, arranged in a complex three-dimensional pattern. Most matter in the universe is concentrated in the filaments and walls. The voids are mostly empty, by which we mean they contain mostly only dark matter and small numbers of galaxies. Most voids in the cosmic web are not as large as the KBC void. The typical void scale is 100 to 200 million light-years across. Larger voids exist, but they become increasingly rare as you go to larger scales. A 1 billion light-year void is, by current cosmological models, an outlier. This is one of the puzzles. The KBC void, if real, is larger than what the cosmological models predict should exist with reasonable probability. The standard model says voids of this scale should be very rare. We seem to be in one. The resolution of the puzzle has several candidates. The void may not actually be as large as it appears. The void may be a statistical fluke. The cosmological model may be wrong about the rarity of large voids. The cosmological model may be wrong about other things, and the void is one of the symptoms. The debate continues. Let me hold this for a moment. Cosmological models, like other scientific models, are built on assumptions. The assumptions are, broadly, that the universe is homogeneous, isotropic, and well described by general relativity with appropriate matter and energy content. The assumptions allow us to write down equations and solve them. When the equations predict that something should be rare, and we observe that thing to be present, one of two things is happening. Either we are seeing a rare event, or the equations are wrong about the rarity. For the KBC void, the question is which. We are, in some sense, the test case. If we are in a rare void, the model is fine, but our location is exceptional. If voids of this size are common, the model is incomplete. The way to distinguish the two cases is to look at the universe more carefully. Other observers elsewhere may also be in voids. If we can find other voids of comparable size, the model may need revision. If we cannot, our location may indeed be exceptional. The search is ongoing. The Vera Rubin Observatory, the DSE survey, the Euclid mission, and other large-scale surveys are mapping the universe at scales and depths that will, in the next decade, give us much better constraints on the actual distribution of voids. What we will find, we do not yet know. Let me hold the rarity of voids of this size for a moment. The standard cosmological model predicts the distribution of voids based on the initial conditions of the universe and the subsequent dynamics. The prediction is that voids of various sizes occur, with smaller voids being much more common than larger ones. The probability distribution of void sizes, in the standard model, drops rapidly with size. Small voids with radii of tens of millions of light years are common. Medium voids, with radii of hundreds of millions of light years, are less common but still occur in significant numbers. Large voids with radii of approaching 1 billion light years are rare. A void with the radius and depth of the KBC Void is, by the standard model, approximately a 6 sigma event. The probability of a randomly placed observer finding themselves inside such a void is, by some calculations, less than 1 in 100,000. This is the puzzle. We seem to be in a 6 sigma void. Either we are statistically very lucky, or the standard model is wrong about the rarity of large voids. The two possibilities have different implications. If we are simply lucky, the standard model is fine, and the universe contains, at any given moment, only a small number of observers in such voids. We happen to be one of them. If the standard model is wrong about rarity, then large voids are more common than predicted. The cosmic web is, in some sense, lumpier than the model assumes. The cosmological principle holds more weakly than the model assumes. Distinguishing between these possibilities requires more data. Specifically, it requires mapping more voids and comparing their statistics to the model predictions. The Vera Rubin Observatory, the DSE survey, and the Euclid mission will all contribute to this work over the next decade. What we will find, we do not yet know. Now let us turn to a different aspect of the story. I want to walk through what the universe looks like on the scales we have been discussing. In order to give a clear picture of where the KBC Void fits, the smallest scale of cosmic structure that matters for this story is the galaxy. A galaxy contains typically tens of billions to hundreds of billions of stars, plus gas, dust, and dark matter. The Milky Way is, in this sense, a large but ordinary galaxy. The next scale up is the galaxy group. Our galaxy is part of the local group, which contains about 80 galaxies, dominated by the Milky Way and Andromeda, plus a few dozen smaller satellites. The local group spans roughly 5 million light-years. The next scale up is the galaxy cluster. A cluster contains hundreds to thousands of galaxies in a gravitationally bound configuration. The nearest large cluster to us is the Virgo cluster, about 60 million light-years away. The next scale up is the supercluster. A supercluster contains several galaxy groups and clusters in a loosely bound configuration. Our supercluster is the Virgo supercluster, which contains the local group, the Virgo cluster, and many other groups. It spans roughly 100 million light-years. The Virgo supercluster is itself part of a larger structure called the Laniakea supercluster, identified in 2014 by Brent Tully and colleagues. Laniakea spans roughly 500 million light-years and contains the Virgo supercluster plus several neighbouring superclusters. Above the supercluster scale, the universe becomes increasingly uniform. The filaments of the cosmic web stretch between superclusters. The voids occupy the spaces between filaments. The largest voids are roughly the size of the largest superclusters, perhaps a few hundred million light-years. At scales of 1 billion light-years, the universe is supposed to be uniform. The cosmological principle is supposed to hold. The KBC Void at 1 billion light-years across is the scale at which uniformity should be the norm. But it is not. We are in an underdensity at this scale. The implications, when we sit with them, are significant. They suggest that the universe is not as uniform as our models assume. They suggest that we may, in our local volume, be in a region that is somewhat exceptional. They suggest that our cosmological measurements may need to be reinterpreted in light of our local environment. The work is ongoing. The picture is evolving. Stay with me here. Now let me bring that closer in a different way. I want to walk through what it means for our position to not be at the centre of any meaningful structure. For most of human history, the geocentric model placed Earth at the centre of the cosmos. The sun, the planets, the stars, all revolved around us. The model was wrong, in retrospect, but it served as a useful framework for many centuries. The Copernican revolution in the 16th century displaced Earth from the centre. The sun took the centre. We orbited the sun. The understanding of stars as suns accomplished in the 19th and 20th centuries displaced the sun from any special position. Our star became one of many. The galaxy then became the centre. The understanding of galaxies as one of many, accomplished in the early 20th century, displaced our galaxy from any special position. We became one galaxy among billions. The cosmological principle formalized in the 20th century displaced any particular location from special status. The universe on large scales was supposed to look the same from anywhere. The KBC Void, if real, partially reverses that last step. Our location, while not the centre, is somewhat distinctive. We are in an underdense region. Other locations, elsewhere in the universe, would have different local environments. We are not at the centre of anything. But we are, in some sense, in a particular kind of place. This is, in some ways, a return to a more nuanced view of our cosmic position. We are not at the centre, but we are also not in a perfectly average location. We are somewhere with particular properties. The particular properties matter because they affect our measurements. They affect what we see when we look out at the cosmos. They affect, in subtle ways, our entire cosmological picture. Hold this. Let me also walk through what this means for our understanding of cosmic time. The universe has been evolving for 13.8 billion years. The structures we see today are the products of that evolution. The cosmic web has been growing throughout cosmic history. Voids in this picture are the original underdensities that have been growing as the universe expands. The KBC Void started, in the early universe, as a slightly underdense region. Over 13 billion years, the underdensity has grown into the void we observe today. This is the cosmic history of our location. The original primordial slight underdensity grew, gathered, evolved until it produced the void we now inhabit. The Milky Way, when it formed roughly 10 billion years ago, formed in the early stages of this void. The Sun and Earth, when they formed 4.5 billion years ago, formed in a slightly more pronounced version of the void. We, observing the void today, are observing it in its current, more pronounced form. The void will continue to evolve. It will grow. It will become more pronounced. The Milky Way will continue to be in it. This is the long arc of our cosmic location. We have always been in this void. The void has shaped, in subtle ways, the formation and evolution of our galaxy and our solar system. The void will continue to shape in subtle ways our cosmic future. Let me hold what this means for our specific history. Our galaxy formed about 10 to 12 billion years ago in the early universe. The KBC Void at that time was less pronounced than it is now. The underdensity was beginning to develop. The cosmic web was in early stages of assembly. Over the subsequent 10 billion years, the galaxy has evolved. Stars have formed, lived, and died. Planetary systems have assembled. The Sun and Earth formed about 4.5 billion years ago. Life arose on Earth perhaps 4 billion years ago. Complex life perhaps 1 billion years ago. Humans perhaps 300,000 years ago. Human civilization perhaps 10,000 years ago. Modern cosmology perhaps 100 years ago. The KBC Void has been growing throughout all of this. It started as a small primordial underdensity. It is now a 1 billion light-year region of slightly suppressed matter. It will continue to grow, slowly, indefinitely. We are, in some sense, observers of a long cosmological process. The process began before our solar system. The process continues after our civilization will have ended. The process is impersonal. It does what it does, regardless of our presence. What we have done, in our small recent moment, is begin to notice it. We have built instruments. We have collected data. We have identified the void. We have begun to understand its implications. The noticing is ours. The cosmic process is the universe's. This is the relationship. The cosmos does its work. We watch, we measure. We try to understand. The understanding, when it comes, will be partial. The understanding will be local. The understanding will be, in some sense, exactly what we can extract with the instruments and the time we have. But the understanding will, eventually, be substantial. We will know in time much more about our cosmic position than we know now. The work will accumulate, the picture will sharpen. The picture, when we sit with it, is one of localized cosmology. The universe at large is one thing. Our local volume is, in some particular ways, slightly different. The differences are small. The differences are real. The differences may, when we account for them, resolve some of the tensions we currently observe. Or they may not. The picture is still developing. Now let me sit with the question of what the KBC Void implies for our long-term cosmological future. The universe is expanding. The expansion is, by current measurements, accelerating. Galaxies that are not gravitationally bound to us and that are sufficiently distant are receding from us at speeds that exceed the speed of light. The space between us and them is expanding faster than light can cross it. They are, in a real sense, drifting beyond our reach. This is the broad pattern of cosmological expansion. It has been with us for most of cosmic history, and it will continue indefinitely into the future. If we are inside the KBC void, the local expansion rate is higher than the cosmic mean. The galaxies inside our void are receding from each other slightly faster than they would in an average region. The void is, in some sense, expanding faster than its surroundings. The void is, in this picture, slowly growing. Over cosmic time, the boundaries of the void move outward. The underdensity becomes more pronounced. This is, in some sense, the natural fate of voids in an expanding universe. They expand, they become emptier. The matter they contain spreads out further. The boundaries move outward into the surrounding higher density regions. For us inside the KBC void, this means that our local cosmic environment is, over time, becoming less dense relative to the cosmic average. The trend will continue, slowly, indefinitely. Our cosmic neighbourhood is becoming, in a relative sense, emptier. Let me also walk through one more aspect of the void picture, which has to do with structure formation. In the standard model of cosmology, structure forms hierarchically. Small structures form first. Larger structures form by mergers and accretion of smaller ones. The process continues throughout cosmic history, with each generation of structures incorporating smaller predecessors. In an underdense region like the KBC void, structure formation has been slightly suppressed. The lower density means that gravitational collapse proceeds more slowly. Fewer galaxies form. The galaxies that do form are, on average, slightly less massive. The clusters are, on average, slightly less rich. This is consistent with what we observe in the void. The galaxy counts are lower. The cluster sizes are slightly smaller. The matter distribution is somewhat less developed than in the cosmic average region. The Milky Way is, in this picture, a galaxy that formed in a slightly suppressed environment. Our local cosmic context is, in some sense, less developed than a typical cosmic context. We have fewer cosmic neighbours. The neighbours we have are, on average, slightly less impressive than they would be elsewhere. This is, again, a subtle effect. It does not produce dramatic visible differences, but it is real, and it affects the statistics of our local population. We are in a slightly underdeveloped cosmic neighbourhood. The neighbourhood is fine, by any practical measure. The neighbourhood is simply not the cosmic average. We have what we have. We work with what is here. This is not, I want to emphasise, dramatic. The rate of change is slow. Over the timescales of human civilization, the change is negligible. Over the timescales of cosmic evolution, the change is significant but gradual. It is one of the long-term features of our cosmic position. The void persists. The void grows. The void shapes our future, in subtle ways, over very long timescales. Now let us hold the philosophical aspect for a moment. What does it mean to live in a cosmic underdensity? The first thing it means is that our local environment is somewhat exceptional. We are, in some sense, in an unlikely place. Most random observers in the universe, on average, would not be in such an underdense region. The second thing it means is that our cosmological measurements are biased by our local environment. We need to account for that bias when extracting cosmic parameters. The third thing it means is that the universe is more complex than the simplest models assume. The cosmological principle, while broadly correct, has subtle violations at observable scales. The simplest models do not capture all of the structure. These three implications taken together paint a picture of a universe that is somewhat lumpier than the simplest models predict. The lumpiness is not enormous. The lumpiness is, however, real. The lumpiness affects what we see and what we measure. The implications for our scientific understanding are significant. The implications for our philosophical understanding of our place in the cosmos are also significant. We are not at the center of anything, but we are, in some sense, somewhere particular. The particular location matters. Stay with me here. Let me hold one more thought about the philosophy of this. We've been talking, throughout this evening, about our particular cosmic location. The location is, by current evidence, in an underdense region. The underdensity affects our measurements. What this means, in some sense, is that the universe is not a uniform abstraction we can study from any point. The universe is a richly structured environment with particular features at particular locations. We happen to be at one such location. Other observers elsewhere would be at other such locations. This is a more nuanced picture than the simple homogeneous universe. It is more local in some sense. It is more anchored in our particular cosmic geography. But the universe is still vast. The universe is still ancient. The universe still operates by the same physics in every direction. The general principles of cosmology still apply. Only the local details of our environment are particular to our location. We sit in our small particular cosmic neighborhood. We do our cosmology. We extract the cosmic parameters with appropriate care. We add to the cumulative human understanding of where we are. This is what we have been doing. This is what we continue to do. Let me also walk through what the universe looks like at scales much larger than the KBC Void, because the KBC Void is large by familiar standards, but it is still a feature of the local universe, not the global universe. At scales of 1 billion light-years, the KBC Void is one structure. At scales of 10 billion light-years, the void becomes one of many features in the cosmic web. At scales of the full observable universe, roughly 46 billion light-years across, the void is a small ripple in a vast distribution of matter. The observable universe contains, by current estimates, hundreds of billions of galaxies. Most of those galaxies are outside our local underdensity. Most of them are in regions where the matter density is closer to the cosmic average. Some are in overdense regions like superclusters. Some are in other voids of various sizes. The cosmological principle, applied at the scale of the observable universe, holds. The matter distribution averages out to roughly the same density in any direction we look. The cosmic microwave background is highly isotropic. The cosmic web, while structured at smaller scales, is statistically uniform at the larger scales. This is consistent with the KBC Void being a real feature of our local environment, without violating the cosmological principle on the larger scales. The void is a small ripple on the cosmic background. The ripple matters for our local measurements. The ripple does not change the global picture. So when we say that the cosmological principle holds, we mean it holds on the larger scales. We do not mean it holds perfectly at our local scale of 1 billion light-years. The KBC Void is one of the deviations from perfect homogeneity at intermediate scales. There are presumably many other such deviations elsewhere in the universe. We happen to be in one. This is the picture. Local inhomogeneity, global homogeneity. The two are not in conflict. They operate at different scales. Now let me walk briefly through some of the alternative explanations for the Hubble tension, which the KBC Void hypothesis competes with. The first alternative is new physics in the early universe. The standard model assumes a particular history for the early universe, beginning with the hot, dense Big Bang, transitioning through nucleosynthesis, recombination, and the formation of structure. Some proposed modifications add new particles or fields to the early universe that affect the cosmic microwave background in ways that change the inferred Hubble constant. Examples of such modifications include early dark energy, which is a hypothetical form of dark energy that was active in the very early universe, but has since become negligible. Sterile neutrinos, which are hypothetical neutrino species with no standard model interactions. And modifications to the speed of sound in the cosmic plasma, which would affect the size of acoustic features in the cosmic microwave background. Each of these proposed modifications has been investigated. None has been definitively confirmed. Some are more consistent with the data than others. The work continues. The second alternative is new physics affecting dark energy. The standard model assumes that dark energy behaves like a cosmological constant, with constant energy density throughout cosmic history. Some proposed modifications allow dark energy to evolve, perhaps having been more important in the past or becoming more important in the future. Evolving dark energy could, in principle, affect the inferred Hubble constant by modifying the expansion history. The DESI survey, which began full operations in 2021, is producing data that constrains dark energy evolution. The first results released in 2024 hinted at modest dark energy evolution. The hint has not yet been confirmed. Subsequent data releases will refine the picture. The third alternative is systematic errors in the distance ladder. The local Hubble measurement relies on a chain of distance determinations, beginning with parallax measurements of nearby stars and extending outward through Cepheid variables to type II supernovae. Each step in the ladder has its own uncertainties. The cumulative uncertainty, while small, is not zero. Some calculations have suggested that systematic errors in particular steps could account for the Hubble tension. Other calculations have rejected this possibility. The work continues, the methods are being refined. The fourth alternative is the local void hypothesis, which is essentially the KBC Void picture. As I have walked through, this hypothesis says that we live in an underdense region that biases our local Hubble measurement. Each of these alternatives has its supporters in the field. None has been definitively confirmed. The Hubble tension remains, at this writing, one of the active mysteries of modern cosmology. The resolution, when it comes, will tell us something important about the universe. Either we will need new physics, or we will need a better understanding of our local environment, or we will need a combination of both. Stay with me here. Let me also walk through what the cosmological principle is and how the KBC Void interacts with it. The cosmological principle, in its modern form, states that the universe is homogeneous and isotropic on large enough scales. Homogeneous means that the universe looks the same at every location. Isotropic means that the universe looks the same in every direction. The principle is, in some sense, a working assumption rather than an established fact. It allows us to write down the equations of cosmology in a tractable form. Without it, the equations would have spatial variations everywhere, and they would be much harder to solve. The principle is, however, observationally constrained. We have data that supports it. The cosmic microwave background is very nearly isotropic, with variations of only 1 part in 100,000. The large-scale distribution of galaxies, averaged over the largest scales we can survey, is approximately uniform. The Hubble flow, on average, is the same in all directions. But the principle is not exact. There are small variations at every scale. The cosmic microwave background has anisotropies. The galaxy distribution has voids and filaments. The Hubble flow has small directional variations. The question in modern cosmology is at what scale the universe becomes truly uniform. Below that scale, there are structures and inhomogeneities. Above that scale, the cosmic average dominates. For most of the past century, the assumed scale of uniformity was a few 100 million light-years. The cosmological principle was supposed to hold at scales above this. The KBC Void, at 1 billion light-years across, suggests that the scale of uniformity may be larger than previously thought. Or, alternatively, that the cosmological principle holds only weakly at these scales. This is, in some sense, a subtle but profound revision. The cosmological principle has been one of the foundations of modern cosmology. Modifications to it, even subtle ones, can ripple through to other aspects of the model. The work of understanding the KBC Void is, in some sense, the work of understanding how the cosmological principle actually holds in our universe. The principle may hold at scales somewhat larger than the KBC Void. The principle may hold less strictly than has been assumed. The principle may be, in some configurations, the source of the Hubble tension itself. These are open questions. The work continues. Let me also walk through the historical development of how we understand the cosmic web. The cosmic web, as a concept, is relatively recent. For most of the 20th century, the dominant picture of the universe was much simpler. Galaxies were thought to be roughly uniformly distributed, with small clusters and groups providing local variation. The first hints of larger-scale structure came in the 1970s, when the first galaxy redshift surveys began to map the three-dimensional distribution of galaxies. The early surveys, small by modern standards, hinted at filamentary structure, but did not have the statistical power to map it in detail. In the 1980s, the Center for Astrophysics Redshift Survey at Harvard produced the first three-dimensional map of a significant portion of the local universe. The map revealed the cosmic web in unmistakable form. Filaments stretched between galaxy clusters. Voids occupied the spaces between filaments. The universe, on scales of hundreds of millions of light-years, was structured. The discovery was, in some sense, a profound revision of the simpler picture. The universe was not uniform on these scales. The universe was structured. The structure was hierarchical. Galaxies clustered into groups, groups clustered into clusters, clusters connected by filaments, filaments separated by voids. In the 1990s, larger surveys confirmed the picture. The cosmic web became a standard feature of textbooks. Theoretical models based on simulations of dark matter evolution reproduced the observed pattern. In the 2000s, the Sloan Digital Sky Survey produced maps of unprecedented detail. The cosmic web was mapped out to redshifts of half. The structure was clearly visible. The voids and filaments were characterized statistically. In the 2010s, deeper surveys extended the picture. The local underdensity that became known as the KBC Void was identified in 2013. Other voids and filaments were mapped at various scales and distances. The cumulative picture, by the late 2010s, was a richly structured universe, with the cosmic web as its dominant large-scale feature. We had moved from the simple uniform picture to the structured web picture in roughly 40 years. The KBC Void is the largest internal void identified in this picture. Our local volume is, by current evidence, in such a void. The implications, when worked through, touch the foundations of modern cosmology. Now let me come back to the void. I want to spend some time on what the structure of the void actually looks like, from the inside, because the void, while statistical in its identification, is composed of real galaxies, real gas, real space. Inside the KBC Void, the matter density is about 70% of the cosmic average. This means that, in any given volume, there are fewer galaxies than there would be in an average region. The galaxies that are present are, broadly speaking, the same kinds of galaxies you find anywhere. There is no special class of galaxies that lives only in voids. The galaxies in the void are distributed in their own filaments and clusters. The cosmic web continues inside the void, just at lower overall density. The largest structures inside the void include the local group, the Virgo cluster, the Hydra Centaurus supercluster, and various smaller groups and clusters. These structures are part of the larger picture of the KBC Void. They are the gravitating clumps within the underdensity. They are where most of the matter in our local volume is. Between these structures, the space is, by cosmic standards, relatively empty. The intergalactic medium contains diffuse gas, dark matter, and the occasional drifting galaxy. The space is not vacuum, but it is sparse. This is what living in a cosmic underdensity looks like in practice. The local universe contains the structures it would contain in any region. The structures are slightly fewer in number. The space between them is slightly emptier. The difference at any given location is subtle. You would not notice the underdensity by looking at the sky from any particular planet. The number of galaxies you can see with a sufficiently powerful telescope is determined by the local population. The local population is somewhat lower than the cosmic average, but not by a factor that would be visually obvious. The underdensity is identified only by careful counting and statistical comparison. It is a feature of the cosmic web that has been extracted by patient observational work. Hold this. The KBC Void is, in this sense, a quiet feature. It does not announce itself. It does not produce dramatic visual effects. It is a region of slightly lower density that we live inside, identified by careful statistical analysis of the matter around us. Let me also hold one more time the question of what it means to be in a void, because the word void can suggest emptiness, absence, nothingness. The KBC Void is none of those. The void is, by careful measurement, about 30% below the cosmic average in galaxy density. It contains galaxies, gas, dust, dark matter. It is, by every meaningful measure, populated. Less densely populated than the cosmic average, but populated nonetheless. If you stood on a planet inside the void, the sky would look much like any other sky. The galaxies you could see in your local neighbourhood would be the galaxies that exist in your local neighbourhood. The number of visible galaxies integrated over the whole sky would be slightly less than what an observer in a more average region would see, but the difference would be subtle. It would not be apparent without careful counting. The void, in this sense, is a statistical feature. It is identified through careful counting and comparison to expected values. It is not, in any everyday sense, a feature you would notice. The implications of the void are, however, significant. They affect our local measurements of cosmic parameters. They may resolve some of the tensions in modern cosmology. They redraw in subtle ways our picture of where we are. The redrawing is not dramatic. It is, in some sense, a small correction to a much larger picture. But the correction matters. The correction affects how we extract cosmic information from local data. The correction affects our understanding of the Hubble constant. The correction affects our understanding of the cosmological principle. We are working through what the correction means. The work continues. Let me hold what it means that this discovery only came about in the last decade. For most of the history of modern cosmology, our local environment was assumed to be representative of the cosmic average. We did our measurements. We extracted parameters. We built our standard model. The assumption of homogeneity was, in some sense, the bedrock on which the model rested. In the last decade or so, this bedrock has been shifting slightly. The KBC Void hypothesis, combined with the growing tension in the Hubble constant, has forced us to consider whether our local environment is, in fact, typical. The answer by current evidence is probably not. This is a significant intellectual shift. It does not invalidate the standard model. The standard model still works with appropriate local corrections. But it does require us to think more carefully about the relationship between our local measurements and the cosmic values we are trying to extract. The shift is part of a broader pattern in modern cosmology. As our measurements become more precise, the small inhomogeneities and asymmetries that the simple model neglects become more important. The next generation of cosmological models will need to incorporate these effects more carefully than the current generation does. This is, in some sense, the natural progression of any precision science. As the measurements improve, the small effects that were previously negligible become significant. The model evolves to accommodate them. The KBC Void is one such effect. It is being studied. It is being characterized. It will eventually be incorporated into our cosmological understanding in a careful and quantitative way. The work continues. The implications, however, are not quiet. The implications, when worked through, touch the deepest questions of cosmology. They touch our understanding of the universe's expansion. They touch our location within the cosmos. They touch the cosmological principle itself. We are walking through what those implications mean, slowly, tonight. Let me also walk through what kinds of evidence might definitively resolve the question of whether the KBC Void is real and large enough to matter. The first kind of evidence is more galaxy survey data. The DESI survey, which began in 2021, is collecting redshifts for tens of millions of galaxies. The data, when fully analysed, will provide much tighter constraints on the local density distribution. Specifically, the data will allow us to map the density profile of our local volume with much higher precision than previous surveys. The DESI data is being analysed in stages. Each year, a new data release brings additional information. The full survey will complete around 2026. By then, we should have a much clearer picture of whether the KBC Void exists in the form Keenan and colleagues identified it. The second kind of evidence is improved distance ladder measurements. The local Hubble constant is, at present, the strongest indication that something unusual is happening with our local cosmology. Improved distance ladder measurements, with reduced systematic errors, will sharpen the picture of the tension. The Hubble Space Telescope and the James Webb Space Telescope are both contributing to this work. The third kind of evidence is independent measurements of the cosmic Hubble constant using different methods. Gravitational wave standard sirens, for instance, provide a method that does not rely on the distance ladder or the cosmic microwave background. The LIGO and Virgo gravitational wave detectors have made a few such measurements. The precision is, at present, low, but it will improve as more events are detected. If gravitational wave measurements settle on a Hubble constant that agrees with the cosmic microwave background value, then the local distance ladder measurement is, in some sense, the outlier. The KBC Void hypothesis would gain support. because the local measurement would be the one needing correction. If gravitational wave measurements settle on a Hubble constant that agrees with the local distance ladder value, then the cosmic microwave background measurement is the outlier. Some new physics in the early universe would be needed. The work continues. The fourth kind of evidence is improved cosmic microwave background data. The Planck satellite, which produced the current best measurements, completed its mission in 2013. Subsequent ground-based experiments, including the Atacama Cosmology Telescope and the South Pole Telescope, have refined certain aspects of the measurement. Future space missions, including CMB-S4 and Lightbird, will produce even more precise data. If the new data confirms the Planck value with higher precision, the Hubble tension will be locked in. If the new data reveals systematic issues with the Planck analysis, the tension may be partially resolved. The work continues. Each of these lines of evidence will, over the next decade or so, contribute to our understanding of the KBC Void and the Hubble tension. The picture should become much clearer by 2035. Or perhaps not. New puzzles may emerge. The picture may become more nuanced rather than clearer. Cosmology, like other deep sciences, has a way of generating new questions even as it answers old ones. What we have at present is the developing picture. The picture says we are in a void. The void may affect our measurements. The matter is being worked out. Now let me sit with the philosophy of all of this one more time. For most of human history, our understanding of our cosmic position has been characterized by displacement. Each generation of understanding has moved us further from any special status. From the center of the universe to one planet among many, to one star system among many, to one galaxy among many, to one observer among many in a uniform cosmos. The KBC Void picture introduces a subtle modification to this trajectory. It says that our location, while not central, is not perfectly average either. We are in a particular kind of place. The place has particular properties. The properties affect our measurements. This is, in some sense, a recovery of particularity. We are not unique, we are not central, but we are somewhere distinctive. Our place has characteristics that not every place has. This is, in some ways, the natural endpoint of the displacement story. The universe is full of locations, each with its own characteristics. We are in one of them. The characteristics of ours are not extreme, but they are not nothing. The universe is varied. We are in one particular variation. The implications for our self-understanding are perhaps modest. We are not at the center of anything, but we are not nowhere either. We are in a particular cosmic neighborhood, with particular features, and the features have particular consequences. This is, in some sense, the most refined picture of our cosmic position that current science can offer. We are in the KBC Void. The void is a feature of our local cosmography. The feature has consequences. We are learning what those consequences are. The learning is ongoing. Now let me bring this closer. The KBC Void hypothesis is, at the time of this recording, an active area of research. The data is being refined, the interpretation is being debated, the implications are being worked out. The most likely outcome over the next decade or so is that the picture will become clearer. We will have better constraints on the size and shape of the local underdensity. We will have better understanding of how the underdensity connects to the Hubble tension. We will have more data from new surveys. The work will not, in all likelihood, be finished in a decade. The work will continue across multiple generations of researchers and multiple generations of instruments. The work is what cosmology does. What we have at present is a tentative picture. The picture is supported by significant evidence. The picture is not yet definitively confirmed. The picture has profound implications, if it turns out to be correct. We are, in some sense, in the middle of finding out where we are. Let me hold this. The middle of finding out is, in some ways, the most interesting position to be in. We have enough data to formulate the question. We do not yet have enough data to answer it. The answer, when it comes, will be a result of continued work over the next several years to decades. We do not know what the answer will be. We have hypotheses, we have evidence. We have careful analyses, we do not yet have certainty. This is the texture of modern cosmology. The most interesting questions are the ones in the middle of being answered. The KBC Void is one of those questions. The Hubble tension is connected to it. Both are active. Both are unresolved. We continue to work on them. Let me hold one more aspect. The KBC Void hypothesis is, at this writing, not the only candidate explanation for the Hubble tension that involves the local environment. There are several variants. The first variant is the simple void picture I have been describing. We are inside a large underdensity. The underdensity biases our local Hubble measurement upward. The cosmic value is the cosmic microwave background value. The local elevated value is an artifact of our location. The second variant involves anisotropic expansion. Even if the universe is, on average, homogeneous, the expansion rate might vary slightly in different directions due to local matter distribution. Some recent analyses have hinted at directional variations in the Hubble flow. If real, these variations would suggest that even the cosmic microwave background value, integrated over particular directions, might differ from the strict cosmic average. The third variant involves bulk flows. Even at scales of hundreds of millions of light-years, galaxies have significant peculiar velocities relative to the cosmic rest frame. Bulk flows of this kind, if persistent over the volumes covered by the distance ladder, could bias the local Hubble measurement. Whether such flows exist at the required level is debated. The fourth variant involves complex three-dimensional density structures. Rather than a simple spherical void, the local matter distribution might have a more complex shape. Filaments, walls, and voids might combine in a particular configuration that produces the observed local Hubble elevation. Detailed modelling of these complex configurations is ongoing. Each of these variants represents a different way that local environment might affect cosmological measurements. They are not mutually exclusive. Some combination of them might be operating. The cumulative picture is that our local cosmography is, in some way, biasing our measurements. The exact nature of the bias is still being worked out. This is the texture of modern cosmology. The picture refines over time. The biases are identified, characterized, and corrected. The cosmic parameters are inferred with appropriate care. The work is patient. The work is slow. The work proceeds across decades. Let me also hold one final thought about the way that this discovery, like other deep discoveries in cosmology, propagates through our understanding. When the KBC Void was first identified in 2013, it was a single paper in a scientific journal. The paper was, for a time, mostly unknown outside the specialist community. The hypothesis was tentative. The implications were not yet fully worked out. Over the subsequent decade, the hypothesis has been refined. Other researchers have built on the original work. The implications have been mapped. The connections to the Hubble tension have been identified. The picture has become more elaborate. This is the typical trajectory for important results in modern cosmology. The initial paper is a small contribution. The subsequent work by many researchers across many years builds the full picture. The final understanding, when it arrives, is the cumulative product of all that work. The KBC Void hypothesis is, at present, somewhere in the middle of this trajectory. The initial work has been done. The refinement is ongoing. The full implications are still being worked out. The final understanding is some years away, but the trajectory is clear. The hypothesis is gaining attention. The data is improving. The interpretation is being refined. The connections to other questions are being explored. In time, the picture will become clearer. We are in some sense watching the slow development of a major piece of modern cosmological understanding. We are not at the beginning of the story. We are not yet at the end. We are in the middle, watching the picture come into focus. This is the texture of where we are. This is what we have been walking through tonight. Now, let me come slowly to a quiet close for tonight. We have walked through what the KBC Void is, how it was identified, what it means, and what its implications are. We have walked through the connection to the Hubble tension. We have walked through alternative explanations. We have walked through the philosophical implications. We have not, at the end of all of this, arrived at a definitive answer. The picture is still developing. The questions are still being refined. What we have arrived at is a more careful question, a more careful understanding of where we are, a more nuanced picture of our cosmic position. We are inside an underdensity. The underdensity extends 1 billion light-years in every direction. The underdensity contains us, the Milky Way, the local group, and many neighbouring structures. The underdensity is, by careful count, about 30% below the cosmic mean. The underdensity may be responsible for the elevated local Hubble constant. The underdensity may not be. The matter is being investigated. This is the situation. This is where we sit. Hold this. We are, in a real sense, in the middle of one of the deepest puzzles in cosmology. The puzzle is about where we are. The puzzle is about how representative our location is. The puzzle is about whether our cosmological measurements need to be reinterpreted. The puzzle has not been solved. The puzzle is being worked on. Now let me pull back one final time. The cosmos, as we have walked through tonight, is a structured place. It contains filaments, walls, and voids, on scales ranging from millions to billions of light years. Galaxies are distributed along the filaments and walls. The voids are mostly empty, by which we mean low in galaxy count and matter density. The KBC Void, if real, is the void we live inside. It is large. It is 1 billion light years across. It contains us. We are slightly off-center. The void was first identified in 2013. The identification has been refined since. The implications have been debated. The connections to other open questions in cosmology have been mapped. Let me hold for a moment of what this means in a broader sense. The discovery of the KBC Void is, in some ways, a humbling result. For most of the 20th century, we assumed that we were in a typical cosmic location. The cosmological principle, with its assumption of universal homogeneity, allowed us to do our cosmology without worrying about local effects. The assumption was working. The measurements were consistent. In the last decade, that comfortable picture has been disturbed. Our local environment, it now appears, is somewhat distinctive. We are in an underdensity. The underdensity biases our measurements. The Hubble tension, which has emerged as a significant puzzle, may be partially or wholly explained by this local environmental effect. This is humbling because it suggests that our cosmology has been, in some sense, partially local. The measurements we have been making from our particular vantage point are not exactly the cosmic measurements we believe them to be. They are local measurements, with local corrections required. This is also liberating, in some sense. The puzzle of the Hubble tension, which threatens to demand new physics, may have a simpler resolution. The simpler resolution is that we live in a particular kind of cosmic neighbourhood and that our measurements reflect that. The work of confirming which is the correct interpretation continues. The picture is becoming clearer over time. What we have at present is the question. We are inside the KBC Void by current evidence. The void affects our measurements. The void may or may not fully explain the Hubble tension. We are working it out. This is the position. This is where we are. Hold this. The work of cosmology is, in some sense, the slow, careful construction of an account of where we are. The account is partial. The account is provisional. The account is being refined as new data comes in. What we have at any given moment is the best account we have so far. The account today says that we are in the KBC Void, that the void is 1 billion light years across, that the void may be related to the Hubble tension, and that the matter is being investigated. In another decade, the account may say something different. The fundamentals may shift, the picture may sharpen, the puzzles may resolve in unexpected ways. That is the nature of the work. We do not have the final account. We have at any moment the working account. The working account evolves over time as we learn more. The evolution is, in some sense, the substance of the science. The science is not the static fact. The science is the process of refinement. We are participants in that process. We are doing our small part. We are listening, measuring, recording. We are adding to the cumulative human understanding of our cosmic context. What we add is modest. What the cumulative effort adds over generations is substantial. We do not individually produce the final answer. We add to the slow, patient growth of understanding. This is the work. This is what we have been doing tonight. We do not yet have a definitive picture. We have a tentative one. The tentative picture suggests that our cosmic position is, in some sense, distinctive. We are in an underdensity. The underdensity is large enough to affect our cosmological measurements. The underdensity may be the resolution to the Hubble tension. The underdensity may not be. The matter is open. What we have is the void. The void is what we live inside. The implications, when we sit with them, redraw our picture of where we are. If you have come here to rest, let this carry you. The void is not threatening. The void is, in some sense, the quiet pocket of the cosmos that we happen to inhabit. The pocket has its particular features. The features are not unusual in any threatening way. They are simply the local properties of our local cosmic environment. The cosmos goes on. The expansion continues. The voids expand. The filaments thicken. The cosmic web evolves slowly, over billions of years, in its endless quiet way. We are in one part of that web. We are, by current understanding, in a slightly underdense region. We are working out what that means. The work continues. Let me hold one more time the specific gravity of what this discovery means, if it holds up. The KBC Void, if real, is one of the most significant features of our cosmological position that has been identified in the modern era. It would mean that our local environment is not, in the strictest sense, typical. It would mean that our cosmological measurements are biased by our location. It would mean that the Hubble constant we measure locally does not equal the cosmic Hubble constant. These are not small implications. They touch the foundations of how we have been doing cosmology. They suggest that some of our most precise measurements are, in some sense, of local rather than cosmic quantities. The corrections required to extract the cosmic values from our local measurements are not yet fully worked out. The corrections depend on the exact size and shape of the void, on its density profile, on the way the void interacts with the cosmic expansion. Each of these inputs is being refined, the data is being collected, the analyses are being done, the picture is becoming clearer, slowly over time. What we have at present is a tentative picture. The picture suggests that we are in a void. The picture suggests that the void affects our measurements. The picture suggests that careful correction may resolve some of the tensions we currently observe. The picture has not been definitively confirmed. The picture is being investigated. We are, in some sense, in the middle of finding out where we are. The middle of the finding out is a particular kind of moment. It is uncertain. It is exciting. It is, in some ways, the most interesting position to be in. We continue. Stay with me here for one more moment. The questions we have been walking through are, in some ways, the most subtle in cosmology. They do not involve dramatic events. They do not involve catastrophes or wonders. They involve careful counting, careful comparison, careful interpretation. The work is patient. The work is slow. The work proceeds across decades and centuries. What we have at any given moment is a snapshot. The snapshot today says that we are in the KBC Void, that the void is 1 billion light-years across, that the void may be related to the Hubble tension, and that the matter is still being investigated. Tomorrow's snapshot may say something different. The data is still being collected. The analyses are still being refined. We continue. Let me hold the timeline of how we have come to know this. In the late 1970s and early 1980s, the first galaxy redshift surveys began producing three-dimensional maps of the local universe. The surveys were small by modern standards. They contained tens of thousands of galaxies. But they began to reveal the structure of the cosmic web. Filaments, walls, and voids became visible. In the 1990s, larger surveys came online. The Las Campanas Redshift Survey, the CFA Redshift Survey, the 2-degree field Galaxy Redshift Survey. Each survey added galaxies to the cumulative picture. The cosmic web became more clearly defined. In the 2000s, the Sloan Digital Sky Survey produced the largest map of the local universe to date. The map contained over 1 million galaxies. The cosmic web was visible in unprecedented detail. The voids and filaments could be characterized statistically. In 2007, the 2DF Galaxy Redshift Survey published results suggesting that the local universe might be underdense relative to the cosmic average. The result was tentative. The statistical significance was modest. In 2013, Keenan, Barger, and Cowie combined data from multiple surveys, applied careful corrections, and identified the KBC Void at high significance. In the years since, multiple independent analyses have confirmed the underdensity at various levels of significance. The exact size and shape are still being refined, but the existence of the underdensity, in some form, is robust. The cumulative picture, after roughly 4 decades of work, is that we live inside a cosmic underdensity. The work has been done by many researchers across many institutions. The accumulated data is substantial. The conclusions are tentative, but reasonably well supported. This is what science looks like when it is working on the deepest questions. Slow, cumulative, many hands across many years, tentative conclusions that, over time, become more robust. Let me also hold one final thread. The investigation into the KBC Void is, in some ways, characteristic of how modern cosmology proceeds. We start with surveys. We make careful measurements. We compare to predictions. We identify discrepancies. We propose hypotheses. We collect more data. We refine the hypotheses. We compare across multiple lines of evidence. We arrive eventually at a tentative consensus. The process is slow. The process is incremental. The process produces, over time, an increasingly refined picture of the cosmos. We are, at this moment, in the middle of that process for the KBC Void. The process is incomplete. The conclusions are tentative. The work continues. This is what science looks like, in its actual texture. Not the dramatic moments of discovery, the slow, patient accumulation of evidence and refinement of understanding. Tonight we have walked through one of those slow processes. We have looked at where we are. We have looked at what we know. We have looked at what we do not yet know. The not yet knowing is, in some sense, the most honest part. We do not yet know if the KBC Void is real in the form Keenan and colleagues identified it. We do not yet know if it fully explains the Hubble tension. We do not yet know what other implications it might have. We are still finding out. The finding out continues. What we have at present is what we have. A tentative picture, a hypothesis with significant support, a puzzle that has not yet been solved. We continue to work on it. Let me walk through one more aspect of the void picture, which is what it implies for our understanding of dark matter and dark energy. Dark matter, as I mentioned earlier, makes up roughly 85% of the matter in the universe. We know it exists from its gravitational effects on galaxies, galaxy clusters, and the cosmic microwave background. We do not yet know what dark matter is, in the sense of identifying its constituent particle. Dark matter is distributed in roughly the same pattern as the visible matter on large scales. The cosmic web is, in some sense, a dark matter scaffold, with visible galaxies marking the densest points. The KBC Void, by extension, is also a dark matter underdensity. The amount of dark matter in our local volume is, by best current estimates, roughly 30% below the cosmic average. Dark energy is a different kind of component. It is a smooth, pervasive contribution to the energy density of the universe that causes the cosmic expansion to accelerate. Dark energy, in the standard model, has constant density everywhere. It is not concentrated in voids or filaments, it is uniform. If we are in an underdensity of matter, both visible and dark, the local dark energy is the same as everywhere else. The ratio of dark energy to matter is, in our local volume, higher than the cosmic average. This is one of the reasons the local expansion rate is elevated. Dark energy plays a relatively larger role in our local dynamics than it does in higher density regions. This is a subtle but important point. The KBC Void is, in some sense, a region where dark energy dominates more than it does in average regions. The acceleration of the cosmic expansion is, in our local volume, slightly more pronounced. Over very long timescales, this matters. The void grows. The underdensity becomes more pronounced. The dark energy dominance becomes more complete. Our local environment moves further toward an empty, dark energy-dominated state. The endpoint in the far future is something like the de Sitter state. The universe expands exponentially. Galaxies recede from each other at ever-increasing rates. The cosmic horizon shrinks, in the sense that the volume of the observable universe from any given location decreases over time. Our voidish position in this picture is somewhat closer to that endpoint than average regions are. We are, in some sense, slightly ahead of the cosmic curve. The future of cosmology, as it plays out in our local environment, will arrive slightly sooner than it does in denser regions. The timescale for these effects is, again, very long. We are talking about billions to tens of billions of years. The effects are subtle on any timescale shorter than that. But the trajectory is real. We are, in some sense, in a slightly accelerated corner of the universe. The slight acceleration will compound over very long times. The void will grow. The underdensity will deepen. Hold this last image. The cosmos is, in some sense, a vast structured place. Our galaxy is in one corner of it. Our corner is, by current evidence, somewhat distinctive. We are in an underdensity. The underdensity extends 1 billion light-years in every direction. This is where we live. This is what we have been walking through tonight. The underdensity is, in itself, ordinary. It is one feature of the cosmic web. The web has many such features: voids of various sizes, filaments of various lengths, walls of various extents. We happen to be in a particular one. The particular one has particular properties. We are, in this sense, in our cosmic neighbourhood. The neighbourhood is what it is. The neighbourhood has been here for a long time. The neighbourhood will be here for a long time more. We are passing through, in our small temporary way, in a particular small moment of cosmic history. What we add as observers is the measurement. We measure. We count. We compare. We make sense of what we find. The making sense is ours. The neighbourhood is the universe's. We continue. The KBC Void is one of the things we have identified in our brief, careful tenure as observers of our cosmic environment. The void is real, by best current evidence. The void is large. The void has implications. The implications are being worked out. We will in time know more. We will in time understand better. We will in time have a clearer picture of where we are. For now, we have the tentative picture. We sit inside it. If you have come here to rest, let the picture carry you. The void is not threatening. The void is, in some sense, just a local cosmic environment where we happen to live. The environment is fine. The environment is ordinary, in the way that ordinary places can be slightly different from the cosmic average. We are in such a place. We sit, we listen, we measure, we record. The work is ours. The cosmos is, in some sense, the universe's, but the measurement is ours. We continue. Let me hold one more aspect: the relationship of the KBC Void to other open questions in cosmology. Beyond the Hubble tension, there are several other open questions in modern cosmology. The nature of dark matter, the nature of dark energy, the mechanism of cosmic inflation, the origin of the matter-antimatter asymmetry. Each of these is, in some sense, a major open puzzle. The KBC Void, if real, may have connections to some of these. The underdensity may affect our measurements of dark matter through gravitational lensing. The underdensity may affect our measurements of dark energy through its impact on the local expansion rate. The underdensity may affect our measurements of the cosmic microwave background through the integrated Sachs-Wolf effect. Each of these connections is being investigated. None has produced definitive results. The investigations are ongoing. The cumulative picture is that the KBC Void is, in some sense, part of the larger puzzle of modern cosmology. The void is not isolated, it connects to other questions. The work of understanding the void is, in some sense, part of the work of understanding the broader cosmos. This is the texture of cosmological research at the frontier. Many questions are interconnected. Progress on one often illuminates the others. The work is, in some sense, a unified enterprise, even though it is carried out by many groups working on different aspects. The KBC Void is one node in this enterprise. The node connects to many others. Working on the void is, in some sense, working on the broader picture. We continue. Now let me come, slowly, to the end of this evening. We have walked through the KBC Void. We have walked through what it is, where it is, what it means. We have walked through the Hubble tension and how the void might be related. We have walked through the philosophy of living in a cosmic underdensity. We have walked through what the implications might be for our understanding. We have not, at the end, arrived at a definitive answer. The picture is still developing. What we have is the question, more clearly seen. The question is whether we are in an underdensity, and if so, what that means for our cosmology. The question is being investigated. The investigation is, in some sense, the work of a generation. It will not be finished tomorrow. It may not be finished in our lifetimes. The understanding will accumulate slowly, over decades, by the work of many researchers, across many institutions. What we have at present is the snapshot. The snapshot says that we are, by current evidence, inside the KBC Void. The void is 1 billion light-years across. The void affects our local measurements. This is, by current understanding, where we are. It is a quiet pocket. It is not threatening. It is, in some sense, the place we happen to live. We are, in the slow, patient way of cosmology, still finding out what living here means. The finding out continues. Let me also walk through the question of what happens at the boundary of the void, because the boundary is, in some sense, the most interesting region. The boundary is where the underdensity meets the cosmic average. The transition is not sharp. The density gradually increases as you move outward from the center of the void into the surrounding higher density regions. The transition extends over hundreds of millions of light years. At the boundary, the matter that has drained out of the void over cosmic time has accumulated in the walls. The walls are slightly denser than the cosmic average, because they have absorbed the matter that would otherwise have populated the void. This is the standard picture of void evolution. The void empties, the walls thicken, the cosmic web becomes more contrasted over time. In our case, the walls of the KBC Void are roughly 500 million to a billion light years from our position. The Sloan Great Wall, identified in 2003, is one of the largest known walls and is at roughly the right distance to be part of the KBC Void boundary. The Sloan Great Wall is a vast filamentary structure containing tens of thousands of galaxies, organized in a sheet-like configuration. We are, in some sense, looking outward from the center of a vast underdensity and seeing the walls in the distance. The walls are populous, the walls contain many galaxies. The walls are where the matter that drained from our local volume has accumulated. This is part of the picture of the cosmic web. We are at the center of a void. The walls are visible at the distances of the largest known structures. The geometry, in some sense, matches. The picture is self-consistent. The KBC Void exists because the cosmic web evolution has produced it. The walls exist because they collected the drained matter. The whole structure is a particular configuration of the cosmic web, one that we happen to inhabit. Hold this last image. The night sky tonight contains, in every direction you look, galaxies that are part of our local cosmic environment. Most of them are inside the KBC Void. Most of them are slightly fewer in number than the cosmic average would predict. The slight fewness is the void. We sit inside it. The galaxies above us, beside us, behind us, are our cosmic neighbours. They are, by our best estimate, a sparser collection than the cosmic norm. We are in a region where galaxies are slightly thinner on the ground. This is not, by itself, dramatic. It is a feature. The feature has implications. The implications are being worked out. We continue. The cosmos goes on. The void grows. The universe expands. The galaxies recede. We sit, we measure, we record. The work is ours. We have, in some sense, just begun to understand where we are. The understanding will continue. The work will continue. The picture will refine. Let me hold one final image. The night sky tonight, in whatever direction you happen to be looking, contains galaxies. The galaxies are part of our local cosmic environment. The environment is the KBC Void. If you could see all the galaxies in the void, the picture would be of a vast structure, populated but sparsely. Filaments, walls, clusters, groups. The cosmic web continues inside the void, just at lower overall density. If you could see beyond the void, the picture would shift. The galaxies would become denser, the walls would thicken, the structure would tighten. We are inside the underdensity. We are looking outward at the slightly denser regions beyond. We are, in some sense, viewing the cosmic web from a particular vantage point. The vantage point matters. The vantage point biases what we see. The vantage point biases what we measure. The vantage point is, in some sense, what makes our cosmology specifically ours rather than the cosmology of a generic observer. We are, by virtue of our location, in a particular kind of relationship to the cosmos. The relationship's not exceptional in any dramatic way, but it is not perfectly average either. The relationship has its own particular features. These features are what we have been walking through tonight. The KBC Void is real, by current best evidence. The void is large. The void contains us. The void affects our measurements. The work of fully understanding the void continues. The work will continue for some time. For now, we have the tentative picture. The picture says we are inside it. The picture says we are off-center but not far. The picture says the void biases our local cosmological measurements. We sit, we measure, we record, we adjust. The work is ours. The cosmos is, in some sense, the universe's, but the measurement is ours. We continue. Let me hold one last image. Right now, in every direction you can look, the galaxies thin out. And for 1 billion light years, in every direction from where you are sitting, there are roughly 30% fewer galaxies than there should be. That is where we live. That is the texture of our cosmic neighbourhood. It is not threatening. It is not exceptional in any dramatic way. It is simply our particular small corner of a vast, structured universe. We sit inside it. We do our cosmology from within it. We make our measurements with appropriate awareness of our local environment. We extract the cosmic parameters with care. This is the work. This is what we have been doing tonight. The void is real, by current best evidence. The void is large. The void contains us. The void affects what we see. We continue to investigate. The picture, in time, will become clearer. For now, we have the working understanding. We are inside the KBC Void. The void is part of our cosmic position. The position has its particular features. The features matter. That is what we have walked through tonight. That is the texture of what we have been doing tonight. Thank you for staying with me through this story.